Hello, this is the 15th class in our Physics of Materials lecture series. In the last class we had a discussion on the history of quantum mechanics, and we will continue with that discussion through this class and then take it forward. So we began last class, I just wanted to summarize a couple of things from there as we proceed forward. We began the last class by looking at some unexplained phenomena at the end of around the year 1900, and amongst them were the Blackbody radiation, discrete nature of atomic and molecular spectra, Compton modified scattering, and photoelectric effect. And we looked in great detail at the Blackbody radiation. It was one of these unexplained phenomena that had been examined, and a theory had emerged for how to explain the data that you obtain from a black body. We looked at what a black body is and how you collect data from it, how the data looks that you get when you get it from a black body. We also briefly discussed the classical way in which people had tried to analyze the data. We looked at the difficulty in explaining the data using the classical approach, and then we looked at the approach that Planck had taken. So what you see on your slide is basically the black body data and the kind of approach that Planck had taken. So Planck had basically, to summarize, he had basically put in this equation E equals h nu, where the idea he was trying to explore, the idea that when you have energy being released by a black body at a certain frequency or being absorbed by a black body at that particular frequency, for that to occur, he said that he just assumed for the moment that there would be a step size involved in this process, and that step size would then manifest itself in the form of a constant h. And so he said excuse me, the energy would be h nu, and he at that point did not know what the value of h would be, and he basically said that so it's some kind of a constant. So this h nu then represents a step size or a quantum, and if nu, the frequency, is very low, then the step is very low. Okay, so the step size is low. So at low frequencies and therefore at high wavelengths here, the step size is very low, and therefore even if the overall energy being supplied to the system or being released by the system is small, even if that overall energy is small, since the step size is small, those modes are active. So those modes are able to participate in this, those frequencies are able to participate in this process. So you see the data available from all of those frequencies. When you get to higher frequencies or therefore lower wavelengths, the nu value is high, and therefore h nu is high, and therefore the step size involved in the release of energy at that particular frequency is now large. Okay, so the h nu is therefore large, and if the overall energy available to the system is small, then the h nu may turn out to be a value that is so high that you are unable to release energy at that frequency. Okay, so it is a matter of the relative quantity of h nu relative to the amount of energy available to the system. So if this is larger than the kind of energy that is available in a shared manner through that system, then that particular frequency will not be participating in that process. So using this idea, he tried to impose this idea just as an approach to see if there was a way to cut off the contribution of higher frequencies and therefore lower wavelengths to the black body radiation process, which is what the data showed. The data showed that at higher frequencies or lower wavelengths, the contribution of those higher frequencies and lower wavelengths appeared to diminish and actually drop to 0 past a point. So he wanted to see what is the way in which you could accomplish this in some kind of a theoretical fashion, and he just made this assumption to see if that would enable such a process. By doing so, he was able to successfully explain this fall off of intensity as you go into of spectral radiance as you go to higher frequencies or lower wavelengths. And initially he did not know the value of h, he just did a curve fit using his theory and assuming some unknown value h for it, and he obtained this value 6.55 10 power minus 34 joules second. With further refinement, today the current accepted value for h is 6.626 into 10 power minus 34 joules second. So you can see that even 100 years ago when he first stumbled upon this theory, he was able to get a value for this constant which is very nearly what we use today. Okay, we will take a moment to even to examine this a little bit more to understand a certain subtle aspect associated with this entire process that Planck has given us now. The point is this h, the Planck's constant is effectively now we accept that this is some kind of a universal constant which we now have which we are able to use since then for a variety of purposes, but the point is it has this value, or in fact this current value which we see here 6.626 10 power minus 34 joule second. So the issue is that this is a very small value, okay. So 10 power minus 34 as you are aware is a very small number, 6.626 10 power minus 34. The subtle point that we should recognize here is that if you look at this equation E equals h nu, if and we accept the idea that h nu represents some kind of a step size relative to which the process will occur. If h had been 0, okay, if in a hypothetical case, if Planck had done all this and in a hypothetical situation he discovered that h actually is 0. If h is 0, then regardless of the frequency, okay, so regardless of the frequency can participate in the process because the step size now associated with that frequency is 0, right. So whatever little energy is available, that frequency can still participate in the process. But since h is non-zero, it is a small number, but specifically it is a non-zero number, okay. It is a small but non-zero number, that is a very specific combination, it is a small but non-zero number, and since it is non-zero, we find that the contribution of specific frequencies or especially higher frequencies is now removed from the picture. So this entire field of quantum mechanics, the entire science of quantum mechanics that has evolved, that was discovered by Planck and then and has since evolved, itself traces itself back to this one specific idea or specific fact that we now accept as a fact, that there is this universal constant h and it is a small number but it is a non-zero number, okay. So it is that is what makes quantum mechanics possible, okay, or rather because it exists that way we are forced to accept quantum mechanics as a manner in which nature exhibits its features, okay. So this h being a non-zero number, that such a h existed and that it is a non-zero number is what Planck enabled us to recognize, and by this process he enabled us to recognize that nature is following this rule, that there is some step size which is involved in all of these processes, which or the quantum as we would call it, and therefore to understand nature, to understand the various ways in nature exhibits itself, we have to accept this quantum, and that is how quantum mechanics has come to be, okay. So to summarize again on this slide, I wish to point out that we have to realize that quantum mechanics is directly related or directly a result of the fact that there is this universal constant h which is a small but specifically a non-zero number. If h had turned out to be 0, we would not really have had quantum mechanics, okay. So we discovered that this whole process exists. So so this is what we did last class, we discussed this in great detail, and I have just summarized it here on this slide for you. So we will proceed forward from here. As I mentioned, one of the other phenomena that people did not have an explanation for was the photoelectric effect. The photoelectric effect, the key features of this phenomena were basically that when you actually had a surface and you had light incident on it, then based on the surface and based on the wavelength of light that you had incident on it, some of the surfaces would eject electrons, okay. So and so this phenomenon was known and it had been studied experimentally, and the generalizations that could be made of the phenomena are listed here. First was that no electrons were ejected regardless of the intensity of the incident radiation unless the frequency exceeded a certain threshold value. So frequency was a very important parameter here, it was not just the intensity, the frequency was much more important than intensity in initiating the process. It did not matter how much intensity you had, if you did not have a certain minimum frequency, no electrons were coming out of that system. The kinetic energy of the electrons ejected kept increasing with the frequency once you cross that threshold frequency, okay. But the kinetic energy remained independent of the intensity, right. So both the release of the electron remains independent of intensity and the kinetic energy of the electron remains independent of intensity, both of them seem related to the frequency. At the same time, even at very low intensities, if the threshold frequency was exceeded, there were electrons being released by the system. So these were the three major features of this phenomenon which is the photoelectric effect. So these three features were studied, and Einstein was able to put together an equation which is what is listed down here, half MeV square. This Me is the mass of the electron, V is the velocity of that electron. So this is the kinetic energy of that electron, and as I said, it seems to be increased with the frequency of the incident radiation. So it is proportional to the frequency, and there is a certain threshold that you have to cross before this occurs. He basically put in so he proposed this equation, half MeV square is h nu minus phi, where phi is the work function of that material, and he used this term here. He not only used the idea that the kinetic energy of the electron was proportional to the frequency, he just threw in this constant which was Planck's constant h nu into this equation, and again he was basically introducing this idea that once again there is some kind of a step size involved here, and he pushed this h here, trying to see if that was the same process that was involved here, and he came up with this equation, and this equation actually fit the data very well. Okay. So so what do we have here? We have an equation here where the kinetic energy of the electron is related to the frequency, specifically in the form of h nu minus some constant value which is the work function of that system, right. So given that we find that this equation fits the data, what is the significance of it? Okay, so once Einstein found that this is the kind of data, that the equation that seems to explain the data, fit the data correctly, what is the significance of this equation? What does it imply? The implication is something like this. It appears that the electromagnetic radiation of frequency nu cannot possess any arbitrary amount of energy. Okay, so once you have a specific frequency for the electromagnetic radiation, for one specific frequency nu, it appears that it cannot have any arbitrary amount of energy. Specifically, it can only possess energies h nu, 2 h nu, 3 h nu, etc. till n h nu. In other words, you could not have 1.25 h nu. If the only frequency available was nu, you could not have 1.25 h nu. You can only have 1 h nu or 2 h nu. So this is what the equation seems to imply. So it appears that if you look at electromagnetic radiation of any frequency nu, it seems like it is behaving as though it consists of 1, 2 or 3 particles or n particles, each with energy h nu. Okay. So electromagnetic radiation of frequency nu behaves as though it consists of 1, 2, 3 or maybe n particles, each of frequency h nu. So this is a big change in the way in which we look at electromagnetic radiation. Okay. So whereas previously we have normally thought of electromagnetic radiation as waves, we suddenly find that there is one phenomenon, the photoelectric effect, where the manner in which the radiation is interacting with the sample leading to the ejection of electrons, that manner seems to indicate that the radiation is actually arriving at the surface and manifesting itself at the surface as though it were a particle. Okay. It had there were 1, 2, 3, 4 particles, each with energy h nu. All of those particles are associated with a frequency nu and are associated with an energy h nu, and it appears that the entire process is occurring that way. So suddenly what was always thought of as a wave seems to display particle like behavior, and these so called particles of light came to be known as photons. Okay. So Einstein, through his equation for the photoelectric effect, introduced this concept of photons, or the equivalent of particles of light. Okay. In the sense that he revealed to us that there are experiments, there are situations where the manner in which electromagnetic radiation behaves is very similar to that of particles, or you could explain the phenomenon if you consider it as particles and treated them as particles. Okay. So those particles came to be known as photons. Incidentally, this is past 1900, but if you go back for more than 200 years earlier than that, Newton himself had proposed that light consisted of particles. He called them corpuscles at that point in time, and so that was his idea more than 200 years before photons came along, and he really was examining that idea in great detail, but all of that fell apart when people discovered interference phenomena and diffraction phenomena. So once the people noticed that in fact light could display interference and it could display diffraction, and that those are phenomena that can be explained if you treat light as a wave, and you can actually calculate all the features that you see in an interference pattern or in a diffraction pattern by treating light as a wave. Once people discovered that, Newton's original idea of corpuscles was dropped. People basically did not think that this was a idea worth pursuing, because there was enough strong experimental evidence that light behaved as waves and did not behave as particles. So with that idea ended, and it 200 years later the idea resurfaced, because there was a new experiment where suddenly light also displayed the phenomenon, displayed characteristics that you would normally associate with particles. So the credit for this remains with Einstein, because although Newton suggested it, he really did not have any specific experimental data to back up his idea, or any theory which would actually a proven theory which would actually support his idea. It was just an idea that he was working on, and so with that it had to be abandoned. But Einstein actually was able to show that there was an experimental data against which this idea of particles, especially taken along with the idea of Planck, that you can have this quanta of energy associated with a radiation of frequency nu. Taking all these together, he was able to show that lights can display particle like behavior, and therefore Einstein gets the credit for reviving this idea that light could behave as particles, and which are photons. Incidentally, I also wish to point out that while Einstein did this, he extended Planck's idea. He took Planck's idea, which Planck had employed for blackbody radiation, and employed it, now took it across to a photoelectric effect, which was the other phenomenon that had not been really explained. There were a lot of people, and we believe including Planck himself, who were quite doubtful whether this was the right way to do it, in the sense they felt that although they had stumbled upon this idea of quanta and such, there was a lot of discomfort on whether or not nature actually behaved this way. It appeared like they had stumbled upon something which was working out conveniently and helping them get good fits for various experimental data, but there was a lot of apprehension that perhaps somewhere fundamentally they were not right about it. Perhaps there was some further underlying theory which would not require this kind of quantization. So there was a lot of discomfort about this idea of quantization. So I think it is particularly important for us to recognize this, because when you and I look at quantization and quantum mechanics, and if for some reason we experience some discomfort in trying to accept it and utilize it as is, we can take comfort in the fact that the greatest scientists of our times that we are aware of also had an equal amount of discomfort in accepting these ideas. So they used it, but somewhere in the back of their mind they were not completely convinced that nature actually behaved this way. So it is with a lot of such thought process that the science evolved. Einstein himself was quite opposed to the idea of how the basic principle of how quantum mechanics existed. He was quite unconvinced that it was the final ultimate truth of a fair bit of the science that we saw. Excuse me. So so that is the story of the photoelectric effect, and for this, of course, Albert Einstein got his Nobel Prize in physics. I am sure you are also aware that Albert Einstein is famous for relativity, the theory of relativity, both the general theory of relativity and the special theory of relativity, but he got his Nobel Prize for this equation, which helped describe the photoelectric effect. So we need to recognize that this is a very profound, we have already seen that Planck got a Nobel Prize, we also see now that Einstein got a Nobel Prize for this work. So these are just indications that what they stumbled upon was something phenomenal. It had not been really recognized. I mean, it had not been recognized till that point, and they completely changed the landscape of science. So he got his Nobel Prize in physics in 1921. Some of the photos you see here are from the Nobel organization's website. If you go there, you can definitely see their lectures. You can see a lot more details of all of these famous people and the work they have done. Alright, so Einstein proposed that light could behave as particles, okay, so or demonstrated characteristics of particles in specific experiments. So that was Einstein's contribution to the quantum mechanics picture. Planck initiated it and Einstein brought forth this idea that light could actually behave like particles. De Broglie, Louis de Broglie, I believe that is how his name is pronounced, he proposed in 1924 that that any particle which was travelling with some linear momentum p could be thought of as having a wavelength lambda, such that the lambda would be given by this equation, okay. So once again you see h, the Planck's constant appearing here, and this is p, the momentum of that particle, right. So you have h, the Planck's constant, and p, the momentum of the particle, and lambda is the result of h by p, okay. So he proposed this idea that any particle, anything that we have conventionally thought of as a particle could have a wavelength associated with it, and this is what it would work out to. And this idea, when I say any particle, in principle you can extend this idea to a particle that is something that is that we can handle. So when you look at, you know, a ball that we are playing with, let us say even a plastic ball, or like what I showed you a couple of classes ago, or any other ball that you find, or any other object, in principle you could use this, if it had a linear momentum associated with it, in principle you can use this equation to see the wavelength associated with it, okay. So it is something that we can extend to life size objects, except that we will find that these wavelengths are not of any great relevance when we talk of life size objects, okay. So that therefore we do not, although in principle this is a concept that we can extend to some larger objects, it is not something that is of any significance in our activity, because it is of a size scale that would be irrelevant to our activity. We would not be sensing it in a physical sense at our size scales. So he came up with this idea, and this was actually proven. It was successfully explored by Davison and Gremmer. They did an experiment where they actually heated a filament which would then emit electrons, and those electrons were then incident on a nickel sample, and they were able to see in a reflection mode the diffraction pattern from that nickel sample, okay. So and as I mentioned before that when you see diffraction or interference, that gives you an indication that you are seeing wave like behavior, okay. So that is because the theory that explains diffraction or interference comes from wave like behavior, okay. So the fact that they were able to see diffraction from a source which was actually giving them electrons then implied that electron was displaying a wave like behavior in that particular experiment. So that is what it implied, right. So what they were able to show is that what we conventionally thought of as a particle, an electron, was actually also capable of showing us wave like behavior, and it so happened that and they were also able to say that, you know, we are able to say with some level of certainty what is the wavelength we can associate with that particle. So they were able to prove this idea of Louis de Broglie and able to establish that his idea of particles also showing that any particle could also show a wave like behavior was actually correct. In fact, incidentally, I mean, as is true with most of, you know, path breaking science, there is some element of luck involved in all of this. The kinds of voltages they used, they did not really know exactly what they were dealing with at that point in time. The kind of voltages they used somehow enabled them to get the diffraction pattern in a manner that they could actually observe, and that really helped them out, and they are pioneers in that sense, and they were able to show that particles can show wave like behavior. So Einstein was able to show that light, or what is conventionally thought of as waves, could show you particle like behavior and Louis de Broglie and Davison Gremmer showed us that what was conventionally thought of as particles, an electron, could show us wave like behavior. So between the two of them, their contribution can be summarized by this phrase here, wave particle duality. So between Einstein and Louis de Broglie, they have successfully shown the world that quantum mechanics and its rules are enabling us to recognize that all waves can show us particle like behavior, all particles can show us wave like behavior. So these are major contributions. Planck showed us that there is this concept of a quantum, Einstein showed us that light can behave like a particle, Louis de Broglie and then Davison Gremmer through their experiments showed us that particles can behave like waves. Sure enough, Louis de Broglie got himself a Nobel Prize for his discovery of the wave nature of electrons, and again you can look up this information in greater detail in the Nobel organization's information. So we now see that we have this people in the about 1900 or so and above and later, people had slowly but surely stumbled upon more and more aspects of quantum mechanics. Okay. So it then turned out that to proceed forward, people recognized that the quantum mechanics was actually accepting within its framework, it was accepting this wave particle duality, and what was previously being thought of as trajectories of a particle were now could also be considered as something that belonged to a wave, and so particle trajectories could now be represented by something called a wave function xi. Okay. So quantum mechanics was encapsulating this idea of a wave particle duality by associating trajectories of particles with a wave function, what is called a wave function, and is represented by this character xi. Okay. Now xi it turns out has the properties of the system, so a particle and whatever else you want to associate with it, that entire system has all its properties are encapsulated by this wave function xi, and it can be obtained by solving the Schrodinger equation, which is what is listed here. Okay. So this is minus h bar square by 2m, this is del square. So h bar is actually h by 2 pi, where h is the Planck's constant, so h bar is simply h by 2 pi. So h bar is minus h bar square by 2m, del square is the operator, this is the potential energy of the system V, this is the wave function xi, and this is equal to E times xi. Okay. So this is an equation, incidentally this is a very famous equation attributed to Schrodinger, where he attempted to see how best you can capture this idea of a wave in the quantum realm, okay, and see what all can you obtain from it, and that is how he examined this xi and came up with this equation. This equation incidentally cannot be derived. Okay, it cannot be derived from any fundamental principles. In fact, it is often described as a not as a derived equation, but as an inspired equation, if you want to call it that. There is no way of formally defining deriving this from more fundamental principles, because this equation itself is the fundamental principle, meaning all it is telling you is that the total energy is the sum of the kinetic and the potential energies. Okay. So kinetic and potential energy contributions contribute to the total energy. It is just put in this form, in this format, that helps us now look at a wave function and see how the wave function is also satisfying this overall situation, right. So so this is how this Schrodinger wave equation is, and in most of quantum mechanics, we start by first considering what are the constraints that the system is facing, and using those constraints we solve this Schrodinger wave equation. Okay. Based on the constraints that the system, typically a particle or a collection of particles, whatever it is that is facing those constraints, we take that system and we solve this, we put those constraints into this equation, typically in the form of the potential, which could be a function of position, and then we solve the Schrodinger wave equation. When we solve the Schrodinger wave equation, we will get a wave function xi. That wave function now belongs to that system and it captures all the properties of the system. So that is how we utilize the Schrodinger wave equation. Right now I am just stating it, when we use it we will see how it is used and how any other features that we need to become familiar with about the Schrodinger wave equation we will see at a little later stage. The Schrodinger wave equation turned out to be a very major contribution, because it really gave us some theoretical framework from which we could actually extract a lot of understanding of the system within the rules of the quantum mechanics. So it really moved the idea of how you handle quantum mechanical systems a distinct step forward, and for this of course he got a Nobel Prize in physics in 1933. He shared that year's Nobel Prize with Paul Dirac, who also made significant contributions to quantum mechanics, and we will see those contributions a little later. And so they shared it for this what is described as for the discovery of new productive forms of atomic theory. Okay, so this is Erwin Schrodinger, and I must point out that the Schrodinger equation, actually what you see here is one version of the Schrodinger equation. Okay, so this is called the time independent version of Schrodinger equation. There is another version called the time dependent version of the Schrodinger equation, and you can see that when you look at the time dependent form of Schrodinger equation, it has conflicts with relativity and theory of relativity. So there is still room to understand what all of that means, but basically this time independent version of the Schrodinger wave equation is what we use for understanding quantum mechanics or for utilizing quantum mechanics. I will also tell you a little bit more about it in a few moments in relation to the contribution of yet another person to the field of quantum mechanics, and at that point perhaps the significance of Schrodinger's contribution will be more clear to us. Right. So Schrodinger wave equation gave us the wave function xi, but there was a lot of confusion on what that xi represented. Okay, so people found out that there was xi, and it seemed to capture a lot of the details of the system. So people were unable to actually tell what is this xi, what is the xi, and what is the, how can you sort of physically understand what xi is. It was a very elusive concept, although xi was there and mathematically you could find it and then you could get information out of it. What exactly was xi was something that people were unable to understand, although it seemed to work well for a variety of purposes. Max Born is credited with helping us come up with an interpretation for xi. He basically said that xi is a wave function, so you can actually have a complex conjugate of it, and xi star dx, or in other words the modulus of xi, square of the modulus of xi times dx, is the probability of finding the electron between x and x plus dx if electron is the system that we are working with. So what he basically said is that when you have a wave function, if you calculate, if you use that wave function and you actually do this calculation for xi star, then depending on xi star dx across the universe, you can calculate it through entire all the space that you have available to you. You will get some picture, some plot you will get. The value of this xi star dx is then an indication of the probability of existence of that electron at that spot. So if xi star dx happens to be a very large value somewhere in space, that means we can say with greater certainty that the electron actually exists at that particular location. If it is virtually 0 at some other locations, it means the electron will most likely not be available at those spots. Okay. So when you look at this is very important, because if you want to understand how electrons exist say within atoms or within a solid and so on, this is the kind of analysis that helps us understand where is the electron going to be. Is it a bound electron, is it a free electron, is it, if it is a bound electron, then you will find a very high concentration in some location, you will not find it in other places, and it will drop to 0 and so on. So understanding what this xi star gives us is a very useful step in understanding what is the electron actually doing in the given the constraints that it has been placed inside. So Max Born's interpretation of the wave function is considered a very significant contribution to quantum mechanics, because it helped us while people were groping in the dark on what is this wave function, even though it seems to work, it helped us put some kind of a physical picture to that wave function. Okay. So this is what his contribution was, and he got a Nobel Prize for this. I am just pointing out that all these people got these Nobel Prizes because I want to highlight the fact, although you may already be aware of it, I wish to underline and highlight the fact that the subject matter that we are dealing with is considered very profound. I mean, although it has been established now over 100 years and people use it and people take many things of it, much of it for granted. The point is, all of these were considered very profound additions to the body of science, and requiring, I mean, considered the highest contributions to the body of science through the years that have gone by, and therefore those people were recognized for these contributions. And it also tells us the kinds of dilemmas that they faced in trying to understand this idea of quantum mechanics, and to see to grapple with this question whether or not nature was really actually following these rules of quantum mechanics, or was there something else that we needed to consider, and so on. So this would help us get a idea of the complexity of the concept of quantum mechanics, at least with respect to how easily or difficult or with how much difficulty we end up having to accept this science as something that is valid. Okay. So the greatest minds of this of the past 100 years or so had a lot of difficulties trying to accept this as the basis of with which nature seems to display its character, and therefore it is not surprising that when we also go through this process, we also at various stages have difficulty in understanding some of this. I will also point out in some of these cases some of the theories where their best guess that this is probably what was happening in the system, and then a check to see if in fact that was happening based on all their knowledge that they had. So in some cases it's difficult for us to actually pin it down to a very specific mathematical process by which the person who came up with the idea actually was able to pin it down to that. So there is some level of abstraction in this and some amount of intuitive leap of faith, so to speak, in trying to reach many of these principles of quantum mechanics, even from the perspective of the people who actually originated this idea. I'll always take you back to this idea that E equals h nu is itself something that Planck himself had a lot of apprehension on whether or not in fact that was the way nature behaved, and that is the basic equation that makes quantum mechanics what it is. Okay, so Max Born got a Nobel Prize for this. The other person who contributed very significantly to the overall field that we are looking at is Niels Bohr. He is the one who actually attempted to look at those atomic and molecular spectra. I mentioned that was another one of those not so well understood phenomena. People did not know why you could not have a continuous spectrum coming out from a atom, why there were discrete lines, why is it that the intensity of the atomic and molecular spectra was very intense at specific locations and virtually zero at other locations, with respect to wavelength. So Niels Bohr suggested this model that you would have a nucleus and you would have electrons going around in fixed orbits, and then when an electron jumps from one orbit to another orbit, there is an energy difference associated with that process, and therefore you would have very specific those are fixed energies, and therefore the difference in that energy would show up as a very specific at a very specific frequency. So this was the idea that he had put forth. Although the eventual understanding of the atoms and the structure of the atoms did not support this idea that you had these fixed orbits, the planetary model was not really the best way of describing electrons present within a solid, but he was still successful in explaining the his approach still successfully explained the spectra that people saw. Incidentally, when I mentioned that Schrodinger actually had this wave equation. So what he did was he looked at the hydrogen atom, which is what Bohr had actually described. So Schrodinger looked at the hydrogen atom, he used the constraints of the electron placed that the hydrogen atom placed on the electron. He tried to capture those constraints in a form that would fit his wave equation, that would be useful for his equation, the Schrodinger wave equation, and he solved for the wave function corresponding to the hydrogen atom with respect to the hydrogen atom, and the result that he got from his analysis was consistent with what Niels Bohr had put out for his theory. So that was considered as a big success for Schrodinger because he was able to show not only show that he had this theory in place which worked, which he had a good reason to believe worked, but he was able to actually compare both with some experimental data, which is the hydrogen spectrum, and also compare well against Niels Bohr's theory for the hydrogen atom, and therefore there is some amount of linkage of these ideas in validating each other, so to speak, and therefore the Schrodinger wave equation then became an even more accepted and agreeable idea, so to speak. Okay, I must also point out that the Schrodinger wave equation, while it works, while we are able to solve it for the hydrogen atom, if you make the system more and more complicated, it becomes more and more difficult to solve the equation. The kinds of mathematical methods and tools you will have to use get fairly sophisticated. So it is not a very easy thing to use, even though the equation itself is very elegantly put. It is not a very trivial thing to actually utilize it for a variety of circumstances. So you will often find in many books the Schrodinger wave equation being solved for simple cases. In fact, for most of this, for our course, we will look at specific conditions and we will solve the Schrodinger wave equation for those conditions, but you will find that you can easily think of conditions which would make the entire calculation process significantly more complicated. Okay, so it is not an easy and straightforward thing to do, and so that is something that you should keep in mind, right. So but it both Niels Bohr and Schrodinger checked out the hydrogen atom and the kind of spectrum that it had and so on, and they found that they were able to I mean independently they were able to see get results that were comparable with each other. Okay, so so Niels Bohr is also credited with having made a significant contribution into the structure of atoms and of the, so as it stated here, for his services in the investigation of the structure of atoms and of the radiation emanating from them. Incidentally, you can see that all of these people actually are I mean have made significant contributions in say the first 2 or 3 decades of after the year 1900, right. So they were all contemporaries of each other, and we will talk of one more contemporary in our next slide. Well, we will talk about that in a moment. This wave function, so anyway they were contemporaries, and we will discuss what they managed to do as contemporaries of each other, and some of the nice things that they were able to work with each other and contribute to each other's work, and how that came about. We will briefly look at the wave function a little bit more. The wave function can be considered as a combination of more than one wave function, each having a momentum. So this was an idea that as people began to accept this wave function, they basically said that okay, the wave function would have a momentum associated with it, and therefore would have and therefore a wavelength and so on. In such cases, and if you had a wave function, you can actually the Schrodinger wave equation may give you a complicated wave function, but we can treat it as a sum of a bunch of other wave functions. Okay, so then it helps us interpret the wave function and the features that we see more conveniently, right. So therefore the meaning of saying that a wave function can then be thought of as a combination of other wave functions is simply that if each of those wave functions has a momentum associated with it, then when you make measurements of the system, in some cases you will get one value of momentum, in some cases you will get the other value of momentum. Okay, so to repeat, if you have a wave function which you can then write as a sum of other wave functions, then you can when you take a random measurement of the system, you will get any one of those momenta associated with any of those wave functions. So this is the what happens when you look at a combination of wave functions leading to the wave function of the system. So a very important contribution of quantum mechanics is based can be understood using this approach. So let us say we would like to localize a particle. Okay, localizing a particle is simply this idea that you now can say with confidence that this particle is in this very narrow region or very narrow location. Like I said, the electron could exist anywhere in the universe, right. So on the other hand, we will say that this electron is now stuck to this very small region which is only say 5 angstroms across, just to give you an example, or even less, maybe 2 angstroms across, 1 angstrom across and so on. So this means the probability of finding the electron in that region should be very nearly 1, and it should be 0 virtually everywhere around it, right. So xi star dx, which I said is the Born's interpretation on what is the probability of finding an electron at a given region, that xi star dx should reach a maximum only in that region and should reach virtually 0 on either side of it. Okay, so if you have such a situation, the xi, the wave function of xi of such a situation where you have a electron that is really localized to one spot would look something like this. It would be virtually 0 everywhere at a very small region corresponding to some particular value of x. You would have a sharp peak, and then it would drop to 0 on the other side also. If you have such a curve, then the xi star dx of this would also looks very similar to this, and that would be consistent with this picture that we have now got the electron localized. So all of this is consistent with the basic concepts of quantum mechanics, right. So we have put this thing together. So what is the consequence of it? To get yourself a wave function like this, what you can do is you can think of it as a sum of series of waves of various different wavelengths, such that they all subtract out on either side of this location, right. So they destructively interfere on either side of this location, and it so happens that all of them constructively or in some way interfere to give you some positive value only in this region, and again destructively interfere on this region, right. So you have a huge number of waves. It will turn out that if you actually do this analysis, the sharper you want to make this peak, the sharper you try to make this peak, you will have to add more and more waves of different wavelengths to enable you to do that. So what do we mean by localizing? By localizing we mean if you what is the error in finding that particle, right. So by localizing we mean that if you look at the width of this location, it will be some small delta x. Localizing means that delta x is as small as you can make it, if you make it smaller and smaller and smaller, it means you are saying with greater certainty that the particle is sitting only in that location, right. So making delta x smaller and smaller is the same is the idea that is captured is the idea that exists when you say that you are localizing a particle. But by doing so you end up having to have wave functions which are of a variety of different wavelengths, and therefore a variety, if you use the de Broglie hypothesis, it amounts to a variety of different momentum, okay, or momenta. So this is what happens, each of those waves wave functions will correspond to a particular momentum. So therefore if you now look at the range of momenta that that particle could have, right, that we can again represent just the way range of positions we represent as delta x, we can represent the range of momentum that it can have as delta p, okay. So so if it can have only one momentum, then delta p is 0. If it can exist only in one position, exactly precisely at one position, delta x is 0, okay. So that is but we say it has a small range over which it can oscillate, so that it has a finite delta x. For it to have a finite delta x, you have to have a very large number of waves with a very large number of momenta associated with them, different momenta associated with them, which will have to add up such that they all subtract out in all other locations except this one location, okay. So therefore making delta x small requires us to make delta p large, alright. So delta x, for delta x to be small, delta p will have to be large. If you make delta p 0, which means it now only has one particular momentum, then you can find that the xi will be such that it will exist, the particle can exist, it will have a non-zero value from minus infinity to plus infinity, and having a non-zero value from minus infinity to plus infinity simply means the electron can exist anywhere from minus infinity to plus infinity, okay. So minimizing delta x will require you to maximize delta p, minimizing delta p will require you to maximize delta x. This idea is captured by this inequality here, delta p delta x is greater than or equal to h by 4 pi, and this is an equation that we now recognize as the Heisenberg's uncertainty principle, okay. So Heisenberg's uncertainty principle is captured in this kind of this equation that you see here, and in fact it is not just this, there are a series of conjugate variables. When you do Fourier transforms, you see these conjugate variables. Any conjugate variable will create this kind of a situation where you will have the variation in one and the possible variation of the other, and the product of them will have to be equal to or greater than a particular value, and therefore if you try to minimize one, the other will go up. It turns out that so in a sense this is actually now a mathematical requirement, okay. So so that is what I wish to highlight here, that Heisenberg's uncertainty principle is now consistent with all the features of quantum mechanics, and it is also in a very fundamental sense it is a mathematical requirement. In many of our high school books we find this description that, you know, if you have an electron and you try to locate its position, you shine a light and that disturbs the electron, and therefore you cannot locate its position very accurately. The more accurately you try to locate its position, you will disturb it and its velocity will change, therefore momentum will change. That description is a simplified description given just to get us going on this concept of uncertainty principle, but it is not an accurate description in the sense it is a misleading description, because it somehow conveys to you the idea that uncertainty principle is simply an experimental limitation, okay. That is the idea that is somehow being conveyed with this kind of a description, that you shine a light and something happens. It is not an experiment, it is not simply an experimental limitation, it is a reality, it is a theoretical reality, okay. It is a mathematical requirement, it is a theoretical reality, because as I said these are conjugate variables and the way they relate to each other will force you to have this inequality. If it were an experimental, if it was simply an experimental shortcoming, then over the last 100 years the uncertainty should have been decreasing, right. There is no decrease in uncertainty. We have had, you know, so much of advancement in experimental techniques. You would have said that, you know, uncertainty was high in the 1920s and is actually very negligible in 2010. That is not the case. Uncertainty is uncertainty and it remains that way, right. Uncertainty principle has not does not fundamentally change. That itself is an indication that this is not simply some experimental limitation that we have to put up with. This is the reality, that the variables, the way they behave are such that you have this inequality, that if you try to reduce delta x, delta p will go up, the error in the momentum estimation, and vice versa. So so Heisenberg's uncertainty principle is very profound in that sense, right. It captures all the essence of quantum mechanics, plus it also tells us what are the limitations and how you can use it. So for this Heisenberg got a Nobel Prize for the creation of quantum mechanics, and this is the way it is described there, but his primary contribution was in this uncertainty principle that he had put forth for us. Okay. And the other major person that we recognize for quantum mechanics is Pauli. He of course is credited with this Pauli's exclusion principle, which is simply that all the quantum numbers cannot be the same for two electrons, and that is something that we use when we understand some of the features of electrons in various solids. I briefly mentioned that one idea a little while earlier, and I just wanted to spend a moment telling you a little bit more about it. All of these people were contemporaries of each other in the first 50 years or so after the year 1900, and they had a lot of discussion on quantum mechanics. They had regular meetings grappling with this idea of quantum mechanics, because many of them, for example Einstein himself was unconvinced that even though they were proponents of this theory, they were very unconvinced that nature behaved this way. They always some of them felt that there was something hidden that they had not yet discovered, and that they would soon discover that nature did not really follow the rules of quantum mechanics, but that has not happened. The more they dwelt on it, the more they analyzed it, the more they were convinced that quantum mechanics is the reality that the world is following in a fundamental manner in all of the aspects that it manifests itself, and so we have to accept it as it is. So if you can read a lot of literature available there, which tells you of all the discussions that people have had, the kinds of meetings that they had, yearly meetings that they had trying to grapple with this, and the kinds of experiments they challenged each other with, thought experiments that they challenged each other with, to try and explain this, to try and get an understanding, better understanding of the either the scope or the limitation of quantum mechanics. So I will finish by this with this summary. These are the major equations that are the essence of quantum mechanics. E equals h nu attributed to Planck, which brought forth the idea of quantization of energy, and therefore the fact that we now had something called quantum mechanics that we had to deal with, and this was then extended by this idea was then extended by Einstein to tell us that light could behave as particles, and then de Broglie then gave us this idea that particles could be treated as waves. So all of that comes here with this de Broglie relationship. Then Schrodinger gave us this idea that now that you are stuck with this concept that there is this wave like behavior and so on, there is a wave function that you can associate with the system from which you can extract all of these properties, and so then therefore we have this Schrodinger wave equation. Born gave us this interpretation for this xi, which is that xi star dx, or this modulus of xi square dx is the probability of finding the electron at x between x and x plus dx, and then Heisenberg gave us this uncertainty principle. These are all the major equations associated with quantum mechanics, and also of course Einstein's contribution. So these are the major equations, and for the purposes that we will use through the rest of this course, we will use these equations as necessary at various stages to help us get better theories and better understanding of how electrons behave in a solid, and what properties of the solid we can now have a much more solid understanding of, much better understanding of, based on the understanding that nature uses these rules. Okay. So we will do this in the subsequent classes. With that we will finish for today. Thank you.